And when are we going to be done with that section?
This week.
What are we going to do after that?
Review for the AP test.
If we all get like above like a 3 on the AP test, can we all get perfects on our test?
I will seriously consider it.
Okay.
Yeah. Seriously consider.
Which funny thing is, I'll probably
better get preparing.
Yeah. So here's my little game plan, because we do have this last section to cover. It's not going to take us that long to do. We're going to do half of it today and half of it tomorrow, and then we'll be done. But this last section, I think, is going to be a good idea for us to do a visual example. I tried to find good pictures to put in your notes so you can actually see what we're going to do, but I think it'd be more beneficial for us if we actually tried to create these figures on our own. So that's what my plan is on Thursday, we're going to play with Play-Doh. We're going to be little kids at heart, okay? We're going to play with Play-Doh, cut paper, okay? We're going to harness our inner child, and we're going to create these 3D shapes. Is that okay for us? Does that sound like fun? Okay. So Play-Doh's already over there. We're going to get to that on Thursday. So my game plan on the board, we're going to finish this section, or work on this section today and tomorrow. Play-Doh activity day on Thursday. And then Friday is our very last free response. And then we're done with all things calculus, at least lesson-wise, okay? After this week, what's that? Review time, yes. So after this week, until May 14th, we're going to be working on practice AP questions and free responses in here every single day, okay? And that's up till test day. Do we remember what we agreed upon after test day?
Is it those tests?
It's the last unit test and the 2 partner quizzes that we skipped from this last unit, okay? So we're going to come back and do those. But if we want to make that wager that we all get 3s or better, I will seriously consider scrapping those, and we'll be good to go.
We do like 1s or better?
Well, that's like 100% guaranteed.
So sounds good.
Sounds good.
We can't lose.
What's up?
Don't we get our scores in July, though?
Yeah.
Can you get them early?
No.
Oh, we can just try really hard.
Try really hard, yeah.
You'll know from the...
I'll know from the eye rolls that come in here, or the like the big sighs, like, oh, I'm so glad that's over. You know, when I can tell by body language when you guys come in here how you felt about it. I'm a good people person. Okay, so we'll think about it, Josh, but we'll see how that goes. Okay?
Do we have the same AP test date?
Yes. Yep. Same test date, same test
What does
time.
he take?
He's taking the Calc 2.
And
There is a Calc 2.
Yes, there is a Calc 2
And stat.
and stats.
Oh, you're taking stats. Oh, that's right. You're in 2 maths. Oh, that sucks.
Technically, you're in 2 maths and I'm in 3.
Oh yeah, because apparently accounting 2 for your senior year can count as a math class.
Really?
I think that's just starting next year though. Or either that or they just didn't tell us that, but yeah.
Accounting 2
Yeah.
counts
If
as a
you
math.
take in the first one and you take accounting 2, your
Yeah.
senior year counts as a math
Because,
course.
I mean, accounting 1 is not really math. It's like
But-
It's not even really a
But
class,
accounting
right?
2 is?
Yeah. Accounting 2 is a little bit more difficult than like you actually have to think.
Well, hopefully we do that every day in every class. But
Yeah, it's not harder than calculus.
No, definitely not.
Calc gets pretty hard.
Calc does get pretty hard. Okay, so in this last section, we're still going to continue talking about volume, but it's not going to be volume in the sense of revolving like we have been doing in the last section. We're going to try to find the volume of a 3D object that has a particular cross section. Do we know what that phrase means? Maybe you've heard of it from like biology or some other course, but do you know what a cross section is? Can you describe it somehow? You have an idea? Yeah.
Like splitting an object somewhere and then like looking at what's showing on the outside.
Okay, yeah.
I was going to say, if you were to split something in half, that's what you would see along the split.
Okay, well, it depends on how you want to split it. Like, for instance, if you want to look at this bottle, do we want to split it this way and then kind of open it up to see what it looks like? or we could rotate it and slice it this way and open it up and see what it looks like. Do we realize how those would be two different shapes? Okay, so I'm going to do this way for a second. If I were to slice this in half and kind of open it up to show you what the inside would look like, can you describe what geometric shape you would see? Yeah.
Like a circle?
It'd be a circle, okay? So that for this particular object, a possible cross-section is a circle, if you were to cut it and look at the shape that it would form. But not everything has a circular cross-section. The first thing that comes to my mind, and I'm going to pronounce it wrong, but it's a type of candy. It's like Toblerone or Toblerone or something. Toblerone. Are we familiar with that? We've seen it. Do you know what the wrapper or box looks like?
Triangle?
If you were to slice it and open it up, wouldn't it look like a triangle, right? Okay, so that cross-section is a triangle. There are some other geometric shapes, but we're going to take a look at squares, isosceles right triangles, equilateral triangles, and semicircles. So if you were to slice some object and kind of open it up to see what the shape would look like, we're going to take a look at these specific cross sections and how we can utilize those cross sections to help us figure out the area of whatever that object is. So for instance, if I wanted to figure out not the area, if I wanted to figure out the volume of this shape, okay, knowing the cross section is a circle, I could utilize that fact in calculus to help me figure out the volume. So we're going to shy away from rotating, because if we rotate, that would be a cross-section of a circle, because you form a circle when you rotate. In these cases, we're going to have different cross-sections. So I want to read this paragraph just for a second and then highlight some key things that we need to look for as we go through these different shapes. So calculus can not only be used to find the volumes of solids created by revolving a two-dimensional area or shape. If we are revolving, aka creating a circle, what was the area of a circle that we integrated in the last section? Remember the area of a circle? Good, Ryan?
Was it pi r squared?
It was pi r squared. Remember how we wrote pi in front of all of those integrals in the last section?
Yeah.
The pi was there because we were integrating the area of a circle. That's because we were revolving, okay? But we might not always be revolving. We might have other geometric shapes that we can use to our advantage. So when it comes time to find the volume, we're simply going to integrate the area of those geometric shapes, whatever they might be. Are they squares? Are they rectangles? Are they triangles? Are they semicircles? As long as we can figure out the area of the shape, we can integrate it to get the volume. Okay, so we're going to utilize that concept today. Now, in these pictures, I tried to get a good angle as best I could. For this first one, do we realize how the trapped area between the two curves is kind of that shape right there? Okay? If you were to imagine, and we're going to do this on Thursday, if you were to imagine measuring the distance between those two functions, almost like drawing in those rectangles that we have been drawing, if you were to measure that distance and cut out a square that had that distance for all four sides, and you were to place that square in the area, okay, we're going to use kind of Play-Doh as the glue on Thursday for that, you could eventually create that 3D figure. The more squares we have, the more realistic it would look to the actual 3D object, because you don't have spaces in between them. But we're going to create that basic shape to it. Did you have a question? No? Okay. So if we're having a cross-section in the shape of a square, we have to first figure out the area of that square, and then we can integrate it. How do you find the area of a square? Go ahead, Josh. Length times width, base times height, okay? But we have to relate that area formula to the particular functions that we're working with. So notice how this square that you might place in that area, its base would be trapped between the two functions. And to figure out that distance that's trapped between those two functions, we simply take the top function minus the bottom function, like we did for area. So if the base has the value of f of x minus g of x, okay, top minus bottom, then all the other sides would have that same value because it's a square. So let's go ahead and, using the concept of length times width for the area, let's go ahead and write the area that this square would have for the function that we would be finding the area in. So that would be f of x minus g of x. That's our length, or the base. And we'd have to multiply by another f of x minus g of x because that's the width, or the height. Can we simplify that expression? Yeah?
We could do f of x minus g of x squared.
Minus g of x squared. Yep, the whole thing squared, because you have f of x minus g of x times itself. So if that's the area of all of these different squares that we might cut out, we have to integrate that area, and that'll give us the volume of the three-dimensional object that we would create. We're just going to use generic bounds like from A to B. So if you can figure out the area of the geometric shape, you can simply integrate it to get the volume. That's what we're going to practice today. All right. So I think the square is kind of easy because it's length times width. They both have to be the same, so you're going to get f of x minus g of x squared. Let's go ahead and try the next one. Okay, so isosceles right triangles. Let's refresh our memory on what isosceles means again. Yeah?
Two sides are equal.
Two sides are equal. Perfect. So maybe I'll go ahead and highlight or draw in here. This is the area that has the trapped region. And what we would do is we would cut out different isosceles right triangles that would have the base and the height being the same distance, kind of like how we have labeled here. Notice how the base is trapped between the two functions, so that's where the f of x minus g of x is coming into play. You have the top function minus the bottom function, bless you. And if it's isosceles, the height would have the same distance because we need to have those two same lengths. How do we find the area of a triangle? Good, Liam? 1/2 base times height. Okay, so let's go ahead and take that area of a triangle and relate it to these different triangles that we were cutting out and placing in that region. So we would need 1/2. The base is f of x minus g of x. And the height would also be f of x minus g of x. It's isosceles, so they're going to be the exact same length. Can we clean up that area formula? Yeah.
It would basically be the same as the square one, but with a 1/2 out front.
With a 1/2 out front. All right. So if that's the area of all of these different rectangles that we would be cutting out, we would simply have to integrate that area formula to help us figure out the volume. And we'll use the generic bounds A to B again. Josh, I think your odds are slim.
I just got 15 minutes and then I can leave.
Yeah. Your odds are slim.
Let me check. We're good as of now.
Do you guys still use aluminum bats, or are they wood?
No, they're aluminum.
They're aluminum. Okay.
Yeah, they're conductors.
Yeah, highly. All right.
Just even with that.
Are we doing okay so far? If we can figure out the area, we can integrate it for volume. Okay. Let's try two more shapes. We'll try an equilateral triangle. What about that word equilateral? Can we refresh our memory? Yeah.
All three sides are the same.
All three sides are the same. Okay, so in our little figure, the base of the triangle is what's kind of trapped or glued in the region. And then we would try to form other triangles that have all the same sides the same. So, right, so if the base is f of x minus g of x, all the other sides would be that same distance. Liam already reminded us that the area formula for a triangle is 1/2 base times height. So let's see if we can calculate the area of this triangle, or all these different triangles that we would draw. So we need 1/2. The base is f of x minus g of x. Do we know the height of that triangle? No. We got to somehow figure out what this length or height is right there. All right, so this is when it's going to get a little tricky. We're going to talk our way through this. Oh boy. Thunder, thunder. All right, we're going to talk our way through this. I don't expect you to remember this process, but we're eventually going to see some type of a connection or a shortcut way to help us remember the area for an equilateral triangle. If all three sides are the same, what else do we know about the triangle? Yeah?
All the angles are 60 degrees.
All the angles are the same, aka 60 degrees. Okay, so let's go ahead and label this angle down here as 60. And by drawing in that height, notice how we're creating a right triangle. All right, so by forming a right triangle, let's go ahead and utilize some trig to help us with this. In relation to this angle 60, notice how the height is the opposite side, and we have the base labeled as f of x minus g of x. So we could utilize tangent to help us with that ratio. So tangent of 60, we would have h over the adjacent side of this right triangle. Okay, but we're only using this left-handed right triangle. What's the distance of the base down here? What do you think, Josh?
1/2 of x.
There we go. 1/2 of f of x minus g of x. Perfect. Okay. Now to save us some time, if you were going to use the unit circle, tangent of 60 would be the square root of 3. And in order for us to figure out h, I'm going to move it over here. In order for us to figure out h, we'd have to multiply the denominator over. So that would leave us with the square root of 3 over 2 times f of x minus g of x. All right, so let's not lose sight of what we're trying to do here. We're trying to figure out the area of this triangle. We already labeled the 1/2, we already labeled the base, and now that we know what the height is, we can go ahead and write that in next. All right, 1/2 base times height. Can we clean that up? Because right now it's just a long, ugly mess. Want to go ahead, Ryan?
Since the f of x minus g of x, since everything is being multiplied,
Uh-huh.
you can combine the f of x minus g of x's into
Yep.
f of x minus g of x squared.
Yep.
And you can combine the 1/2 and square root of 3/2.
Yep.
And get square root of 3/4.
There we go. So there's the area of an equilateral triangle. In order to figure out the volume of the 3D object, we would integrate that. From A to B. I left my umbrella in the car. How sad is that? All right. We ready to move on to the last one? Semicircle? Okay, so a little visual. We have our region. Notice how the diameter of the semicircle is what's placed in that shaded area region, and then you're just forming a semicircle that connects that diameter. How about the area of a semicircle? Good, Liam? 1/2 pi r squared. Perfect. Okay. So let's go ahead and try to figure out what the area would look like for our semicircles, and then we can integrate that for volume. So we have 1/2 times pi, and somehow we got to figure out the radius and square it. What do you think, Daniel?
Radius just be 1/2 of fx minus g.
There we go. So this is the diameter. Okay, we'd have to cut it in half to get the radius. So 1/2 of f of x minus g of x. All right. So let's see if we can clean this up a bit. Notice how we have a 1/2 being squared, so that would change to a 1/4. And if we want to multiply that by the 1/2 out front, that would be a 1/8. Yep. We still have the pi, and it looks like we have another f of x minus g of x squared. So there's the area of all of our semicircles. We can integrate those to get the volume. All right, so these are the 4 common cross sections. There are other ones like rectangles that we might see. Actually, when we do a few examples, we might come across those, but it's still the same process. If you can figure out the area of the cross section, we just integrate it to get our volume. Let's take a look at the bottom of that page. We're going to jot down some nice patterns or things that we might realize. If you were to look at all 4 of those volume integrals that we wrote down, 2 on the front, 2 on the back, do you notice anything in common with all of those? Yeah.
All of them have f of x minus g of x.
All have, not only is it f of x minus g of x, but it's f of x minus g of x squared. Right, all have f of x minus g of x squared. What are the differences between all of those 4? They all have f of x minus g of x squared. But what are some differences? Yeah.
What's outside of that?
What's out front? Okay, what is that multiplier or coefficient in front of that f of x minus g of x squared? Bless you. So this is where I want to jot down some of those coefficients. Okay, we talked about a circle. That was our revolution that we did in the last section. We can also talk about a square. If we have an isosceles, I can spell isosceles triangle. What if we have an equilateral triangle or even a semicircle? Okay, so if we have a circle, what was our multiplier in front? If you think back to the revolutions that we did, what did we write in front of all of those integrals? What's the area of a circle? Pi r squared. So what's our multiplier? What's the pi? That's what we wrote in front of all of the integrals. What's our multiplier for the square? So take a look on the front. What were we multiplying f of x minus g of x squared by? 1, right. What were we multiplying f of x minus g of x squared by for the isosceles cross section? Yeah? A 1/2. What were we multiplying f of x minus g of x squared by for the equilateral triangle? Yeah? Square 3/4. And then for the semicircle? Yeah? 1/8 pi. Okay? So they all have the same setup. They all have f of x minus g of x squared. They're all integrals going from some bound to another bound, bless you. But what's different is what the multiplier is, and that just depends on what cross section you have. Okay, what shape of a geometric object is it? So we're going to utilize those kind of, I guess, shortcuts to help us figure out the areas of some of these cross sections. All right, so let's go ahead and take a look on page 463. We're going to tackle the same region, but we're going to see how the volume is going to change depending on the cross section that we have. Okay, so we have a trig function and a cubic, it looks like. And it looks like our bounds go from 0 to 2. All right, let's see if the cross sections were equilateral triangles. So if you tried to draw those in, you would have your base between the two functions, and you would draw a triangle. Maybe I'll try to do it this way. You would draw a triangle so that all the sides are the same. Now I hope we realize that region R is flat. It'd like be on a piece of paper, and the triangle you draw would be vertical. Okay, like it would be sticking up out of the paper. And when we do this on Thursday, it's going to be a better visual than what we're doing here. Okay, so for cross sections of an equilateral triangle, what is our multiplier? Can we think about it? Reference it? Go ahead, Ryan. Square root of 3/4. Okay, so to figure out the volume, if our cross sections are equilateral triangles, we need to integrate the area. Looks like our bounds would be from 0 to 2. We need a multiplier of the square root of 3/4. And these all should have f of x minus g of x squared, aka top minus bottom. So can we determine what the top function is versus the bottom function? What do you think, Ryan?
The top function is the sine.
Okay, because that's the wavy looking one. Good. And then we have to subtract the entire bottom function. So since you have more than one term, you have to subtract all of that. So all the signs would change. All right, from there it's calculator work. I want you to type it into your calculator and we'll get the volume of this 3D object if the cross sections were equilateral triangles. If you were to cut it and kind of fan it open, it would look like an equilateral triangle. Did you get it? Yeah?
Did you get 1.7?
No, I didn't. Are you in radian mode? Maybe check that because we're dealing with trig.
I'm in radian mode.
You are. Okay, let's check this out.
And we're going from 0 to 2.
Hey, Miss Val,
Hey, what?
Yeah, I did.
Go ahead. Okay.
still not canceling some.
Good luck.
See ya.
You should spit out that answer real quick though.
4.321. Okay, yep. All right.
Oh, yeah, I just square it.
All right, so square root of 3 divided by 4 times, and then we need sine of pi x minus x to the third plus 4x squared. 4.321. Good luck, see ya. 4.321. All right. Can we get it? Calculator being our friend? Okay. Let's do the same area, okay, same functions, but this time our cross sections are semicircles. So if you were to draw that in, this would be the diameter, and then you would have your semicircular shape. What's our multiplier for semicircles? Good, Ryan?
1/8 pi.
1/8 pi. All right, so volume equals, bounds are 0 to 2, multiplier 1/8 pi, and we need f of x minus g of x squared. So again, that's sine of pi x minus x cubed plus 4x. Calculator work from there. Did you get it? Yeah.
3.918.
3.918. With how fast it's raining, it could stop like that. It could just be a quick rain. All right, let's try another one. Still the same region. We're just going to look at a different cross section. This time we have isosceles right triangles. What's our multiplier? A half. Good. Okay, so if you were to draw it, you'd have the base of the triangle would be in the region. The height would be the same length. That's why it's isosceles. And then your hypotenuse would connect those sides. All right. So volume is bounds from 0 to 2. Our multiplier is 1/2. And we need f of x minus g of x squared. Calculator work from there. Did you get it, Daniel?
4.989.
4.989. We're on a roll. All right. Last but not least, cross sections are squares. What's our multiplier? Good, Ryan? Just 1. There we go. So if you were to draw it, base in the region and all of the other lengths would have to be the same. Okay. All right, so volume is 0 to 2. Multiplier is 1, so you don't have to write it if you don't want to. And f of x minus g of x squared. Did you get it, Ryan? Good.
9.978.
9.978. I like it. We doing okay? All right. We're going to stop there for today because talking about the last 2 of them, which are rectangles, might take us some time because we didn't really explore those like we did the other 4. So we'll save those for tomorrow.